So today it's all about whether a number is rational or irrational. So that is our learning target. And by the end, hopefully you'll be able to define that and then be able to pick one out from a lineup. So a rational number, anything that can be expressed as a fraction or a ratio. I got a highlighter, I might as well use it, right? So fraction or ratio is the key to a rational number. Next up, if a fraction is divided out, it would become terminating, so it would end, or it would at least repeat. So again, these numbers are kind of boring because they end or they repeat. So there's something that we know about them that's going to kind of be a common part of that number, all right? Now, an irrational number is something that never ends and never repeats. Now, because of that, you can't write it as a fraction. It's really, the only way to express it as a decimal is to put 3 dots at the end. You're going to see that your calculator can't even show these because your calculator runs out of room and it isn't able to keep going. If not, it probably would never stop. So now that we got the stage set, let's go ahead and take a look at a few of these numbers and state whether they're rational or irrational. Now, this is right below your definition, so hopefully you're using these as we see this. And I'm going to go with my Chinese brush because I don't know. I feel like I have pretty good handwriting with this one. So here we go, 3/4. Well, what do we know about 3/4? It's a fraction. So because it's a fraction, it's a rational number. Okay? First one there. Letter B. Well, this once again is a number with 3 decimal values after the decimal point. So 125 thousandths. And this, because it ends, is another rational number. Maybe I'll change the color as we go here. Next up, letter C. And I probably should put some dividers in here so we can see. 45.14902326. That number is never ending because of the 3 dots, and therefore is irrational. There's our first Karen. She's just not going to stop. She's just going to keep talking, not let that person park. Letter D, we have a never-ending decimal, but it repeats. And we can see that because the 3 is repeating. Now, this is also written as 5.3 with a line over it. So you can see that. Repeating numbers, or decimals for that matter, are rational. The ones with square roots, this was a little tricky for some of us. And why not just go ahead and look at the calculator? So the square root of 36, let's figure out what that is as a integer value or as a number value. So the square root key is second, then the x squared button. So if I press it, it turns to red. And then we're going to put 36 inside the square root. Let's get out of that by pressing to the right and enter. So the square root of 36 is plain old 6. And because of that, we kind of evaluate this and this as the same thing. We've got a rational number here. Okay? An integer for that matter. Now, not all square roots are rational. Let's take a look at the square root of 32. Again, second x squared to get the square root going. 32 inside the square root. Maybe jump out of there, press enter, and voila, 5.65684. 5.65684. And you can see that the calculator just kept going, okay? Now, it doesn't end. I know it may look like it ends here, but that's just the calculator running out of room. It cannot provide any more digits for us. So because we've got a never-ending decimal, it's another one of those irrational numbers that just won't stop. Just keeps going and going. Next up, we've got pi. And let's take a look at the calculator. It does have a pi button. It's the up arrow if you press second first. So second, and then your little caret button gives you the pi symbol. If you press enter, once again, it will give you all the digits of pi. And that is a never-ending, never-repeating decimal. So 3.14156. I've never been one to remember all the digits in pi, but I know there's some people that can recite them for quite a long time. 3 dots to say that it keeps going. Last one, 5.5. We got a mixed number, so whole number out in front and a fraction. Now this is the same thing as if it was a fraction, okay? So fractions are ratios. Ratio is a rational number. It's got it right in there, right? As you kind of see when I pause there. So hopefully that's a... And we're going to see what happens when a rational number is added with a rational, and what happens when a rational number is added with an irrational. Now we can say with 100% certainty, get my highlighter out, that when a rational is added with another rational, we stay rational, okay? But when a rational number is added with an irrational number, the sum will always be irrational. And so we'll make some more sense out of that in just a moment. So here we go with two fractions. We want to find the sum and state whether it's rational or irrational. Well, did you know that if you add two fractions, you're bound to get another fraction, okay? I'm not going to go through the process of creating common denominators and all that. So instead, I'm just going to show you how to do it with your calculator. So 5 divided by 6, that's the best or easiest way to write a fraction, plus 7 divided by 8. Go ahead, press enter, and you're going to get a decimal. Now that decimal is a repeating decimal, the 3 repeats. Remember how to change this to a fraction now. Press the math button, and then the first option is to change that answer to a fraction. So it will do that and be 41 over 24, and therefore is a rational number. Because a fraction plus a fraction makes a fraction, and a fraction is a rational number. Okay? As 7.1, so this is rational, but pi we know is the most famous irrational. So let's take a look at the calculator. 7.1 plus second and the up arrow pi. Press enter, and yeah, it makes it 7.1 bigger, but still never ending, never repeating. So 10.24, 159, and how about 3 dots, okay? Because we get the point. And that is irrational. Letter C has a fraction with a terminating decimal. So because of that, it's going to be rational. You just know that from the start, because a rational plus a rational is still a rational number. With the calculator, again, 11 divided by 3, and we're adding 2.45 just to prove it to ourselves. We get a repeating decimal. Now careful, because of that 7. You're like, oh man, it changes at the end. That's the calculator rounding this. And to prove it, press the math button, change the answer to a fraction, and if it can't, then it's irrational. But because it can, and it's kind of an ugly one, 367 over 60, it's going to be a rational number. Finally, we finish up with a never-ending, never-repeating number, 7932162, plus a regular old 3. I don't even need a calculator for this, because it's just going to add the 3 to the 7. 10.932162, off into the trees here, never-ending. A irrational number. Okay? Because perfect squares are going to be pretty useful when we square root things, because the square root is getting us back to that base. So let's go through some of these quickly, and maybe you can even get ahead of me. 1 squared, 1 times 1, how about good old 1? And 2 squared is 2 times 2 is 4. 3 squared is 3 times 3, which is 9. 4 squared, which is 4 times 4, 16. And I think you're kind of getting the point here. 5 times 5, 25. If you needed to use a calculator, by all means, you could. 6 times 6, 36. 7 times 7, 49. We keep going up the ladder. 8 times 8, 64. 9 times 9, 81. 10 times 10 is 100. And that's usually what students have memorized. But let's kind of push the limits here. 11 times 11, 121. 12 times 12, how about 144? 13 times 13, 169. And then for 14 times 14, just reverse the last two digits there, 196. Okay? Now, you don't have to memorize those, but it certainly helps to kind of keep those in the memory bank. All right? Let's go ahead and look at the next page. And let's go ahead with the first one. Remember, the square root key can be found by pressing second, x squared, and 121. 1, 2, 1. All right? Press enter. And yeah, we get back to 11, right? Because 11 times 11 is 121. So the square root of that, just the root, just the one number, is 11, making this rational. There we go. Square root of 6. Calculator will tell us everything we need to know. So, square root of 6. Press enter. Ah, yes, not so nice. That is 2 points. And let me get my cheat sheet here. 4494. And never ending. So a couple of dots there. Now, because it's never ending, never repeating, we got ourselves an irrational number. Square root of 50 sounds kind of perfect, but it's actually not. No, that's going to be square root of 50, 50. And again, another never ender, never repeater. So 7.071. Let's throw a couple more in there. How about 06? ... Again, irrational. Get off my lawn. Why are you standing there? Last one, 225. We didn't see this one when we were making our list, but if you are good with your multiplication facts, you're going to remember that the square root of 225 is 15. So 15, an integer, a whole number for that matter, something that can be written as a fraction, so rational, because anything can be written over 1 if it terminates. Okay? So there you have when we added and subtracted, we had set rules. A rational plus a rational gave us a rational number. And when we added an irrational number with a rational, we knew it was going to be irrational. Now, when we multiply, something unique happens. Okay? On their own, the square root of the square root of 3 is this irrational number, a never-ending, never-repeating number. And on its own, the square root of 12 is another irrational, never-repeating, never-ending decimal. But you can actually add the square roots together. And now this is an important concept that we're going to use next class, but for right now, just know that we can multiply these together and get the square root of 36. And the square root of 36 is rational. So all of that I've said has been written out for you. So you don't have to, write down any of that as a note. Just understand that a irrational and an irrational multiplied together can sometimes, not all the time, sometimes give you a rational number. So now let's take a look at some examples with this. We want to find the product first. So multiply first, then determine whether it's rational or irrational. So we have the square root of 5 and the square root of 3. That's the square root of 15. Well, let's go to the calculator and type that in. I don't remember that being on my perfect square list, and it's not, because it's a never-ending, never-repeating number. 387,298 for a irrational number. But let's go to 8 times 18. 8 times 18, if you did it in your calculator, is 144. Is that familiar to one of your numbers in your list of perfect squares? It should sound familiar, because the square root of that is simply 12. And that is rational. We take a look at the next two, which is the square root of 77 and the square root of 121. Take a moment now to think about which is rational and which is irrational. Square root of 77, if I put it in my calculator, is going to be a number that's never